Hello and welcome to TN Academy. For today's question, we are given a function h at x is equal to the square root of 4x minus 2 for the interval of x greater than 1/2. Now for the first question, part I, we're asked to find the inverse of the function and state its domain. And then we're asked to find the range of this inverse function. Then for question B, we're asked to find where h intersects with its inverse function. What are the 2 points, the x-coordinates, the roots for this? Then for C, we're asked to find the area enclosed by h and h inverse. And then for D, we're asked to find the derivative of of h. And then lastly, we're asked to find the value of x, which the graph and the inverse have the same gradient. So starting with the first question, we are asked to find the inverse, and the way we can do this is replace x with y in our function. So if we have the function, if we're saying h at x is equal to y, then y would be square root of 4x minus 2. Then we replace x with y so that x is equal to square root of 4y minus 2. And here we've squared both sides of our equation so that the function then becomes x squared is equal to 4y minus 2. Then we can again isolate for y by subtracting or adding 2 to both sides and then dividing both sides by our coefficient in front of the y here, which is 4. Okay, so then we finally find that our inverse is y is equal to x squared plus 2 over 4. Now, to state its domain, we can see the domain is based on the function 4x now is equal to 4x minus 2 must be greater than or equal to 0, which gives us this. The domain of x must be greater than or equal to 1/2. Okay. And now for our second question, we're asked to find the range, and we evaluate our function based on the restriction of our domain to solve for the corresponding y requirement, the requirement of the y value. We get, for our new function, we get the 1/2 squared plus 2 over 4 is equal to 1/4 plus 2 over 4 again. And then we get 9 over 4, which is just 9 over 16, because we multiply these two denominator values. And then we can say that the range shows us or states that y, our function, the y, must be greater than or equal to 9 over 16. Next, we are asked, the graph of h and the graph of the inverse of h to the power of -1, intersect at 2 points. Find these x-coordinates. So, to find the x-coordinates, we first equate the two functions to one another and solve for this equality. So here, what we've done, we've equated the functions to begin. Then we've squared both sides of the equation so we can get rid of this root here because that doesn't help. Then we get 4x minus 2 is equal to x squared plus 2 squared over 16. Now, we have our equality. We have a polynomial in the top now, and we can expand further by multiplying our left side by 16 and then continuing onward to get our final equation where we've simply collected all of our like terms and so forth and simplified. Now to find our roots, though you can use factoring to find a perfect square kind of equation, like in vertice form, at least for one of the terms, there's a perfect square. We can do grouping as well. It's much easier to solve the equation numerically using something like Newton's method. And when doing so, one should find that the 2 points come out to be x is equal to 0.586 and 3.41. Okay? And then for the question C, we're asked to find the area enclosed by h and h to the power of -1. And the way we do this is, for any graph, let's say, For any graph, if we have two functions, I'm going to make them simpler for the sake of ease. If we have, let's just say, even only a linear function, where this is like y is equal to x plus nothing, because, you know, the y-intercept is at 0. The area enclosed is equal to the integral of the function y. So the way we would find the area enclosed by our function is by integrating the two functions with respect to the points of interest, and then finding the absolute difference of the two. So that would look something like this. We're evaluating for the absolute difference of the integrals of h and h to the power of -1. Now, the function does involve two separate cases for the values inside, the absolute values inside of our functions, where we have the integral of h minus h to the -1 for our 2 points, and the reverse case where we have the integral of h to the power of h to the power of -1 minus h, the integrals of them evaluated for the reversed limits. Okay? So, well, I've grouped both of our cases, let's say, for like case 1 and case 2, okay? And again, for simplicity's sake, I'm evaluating the individual parts of our integrals, where we have the square root of 4x minus 2, and the function, or inverse function, x squared plus 2 over 4, let's say. So first evaluating the integral for h, just h, we have the square root of 4x minus 2, and because this is a somewhat complex function, we can simplify it by letting u equal 4x minus 2, so that then we can take the integral of the square root of just u, which is much easier. So again, continuing, we're integrating using substitution. That is the key point here, okay? And if we say u is equal to 4x minus 2, then we have to find du dx, which is equal to 4, and then we find dx, so that we can simply substitute that back into our equation, okay? So then dx, if du dx is equal to 4, then dx is equal to 1 over 4 du. Okay, and then we use the power rule here to solve our equation, where x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1, where, of course, in this case, when we have a square root, we know that n is equal to 1/2. Okay, now substituting our newfound values, u and dx, back into our equation, we get the integral of 1 over 4 square root of u du, and then we can move out our constant 1 over 4 and take the integral of our equation, which gives us 1 over 4 times 2 over 3, because, you know, it would otherwise be divided. 2 over 3 would be in the denominator of our equation, but we've just flipped it and moved it to the front. Okay, and then after we get this equation here, we can sub our u values back into the equation so that we get our final answer, where it's 1 over 4 times 2 over 3 times 4x minus 2 to the power of 3 over 2 plus c. Okay, so that's our first integral. Then for our second integral of x squared plus 2 over 4 dx, we first move out our constant, 1 over 4. Okay, then we're just evaluating the integral of x squared plus 2 dx. And we do this into integrating by parts, where our first integral will be of x squared and our second will be of our constant, 2 dx. We can use the power rule again, as well as the constant rule now, where the integral of ax dx, where a is some constant, is simply ax plus c. So this is actually the integral of a dx is equal to ax plus c. Okay? So our integral then becomes 1 over 4, the constant, times, of course, our whole set of two integrals, our integral becomes the 1 over 4 times 1 over 3x cubed, and our second term becomes 2, our constant times x, so 2x plus c. Just a moment. Now, continuing onward, if we expand the 1 over 4 into our equation, we get 1 over 12x cubed. 4 times 3 is 12. And we get plus 1 over 2 x, because the 2 and the 4 there. Okay. So then we use our two cases, and we will evaluate these functions for the limits. So what? Our first case is the integral of h and h to the negative 1, evaluated at the limit 0.586 to 3.41. So we write out our integrals here, where we have the 1 over 4 times 2 over 3 times 4x minus 2 to the power of 3 over 2 minus our second integral, and we evaluate at 0.586 and 3.41, okay, where we do the integral. So it is of h 3.41. That's not how you would write it. Okay. We do the integral 0.586, 3.41. So the integral of h minus the integral of h to the negative 1. Okay? So that's what I have done here, in fact. So when we evaluate the first scenario at our limits, we get 2 over 3, and this is in the most simplified form, times 20.3581 minus 1.381. And then for a second integral evaluated at these restraints, you get 3.41 cubed plus 2 times 3.41 minus 0.586 cubed minus 2 times 0.586. And then for our second situation, we get the following. Okay, so I'll just give it a moment. Then after, when we plug these two functions, when we plug the values that these two scenarios yield for the absolute value, we find that the area under the curve is equal to 1.89, okay? Now for a final question, we're asked to integrate, or rather find the derivative of h, okay? And to do that, the derivative, we have to use the chain rule because of our function being enclosed by a root. Okay, where the chain rule, we say for dy dx, we will integrate dy with respect to du, y with respect to u, and then u with respect to x, okay? And then we can integrate using the power rule here as well, much like what we did before. So for h is equal to the square root of 4x minus 2, we let u equal 4x minus 2, and then du dx will be equal to 4. Then, of course, we know that dx is equal to 1 over 4 du. Anyhow, moving on, taking the integral of our newfound function, square root u, we then get 1 over 2 root u times du dx, okay, which we've solved and we know is simply 4. So we substitute our variables back into the equation so that we get 1 over 2 square root of 4x minus 2 times 4, so that our final function becomes 2 over the square root of 4x minus 2. Okay? And now for our final question, we are asked to find the two places where the gradients for our equations are equal. Okay? To do that, we have to find the derivatives of h and h to the power of -1 and equate them and solve for their roots, I believe. Yes. So for question in question D, we already found the derivative of h, so we just have to find the derivative of h to the power of -1. Now, here we use the just a moment. Here we technically use the product rule, where for some function, because the reason being h prime is equal to 1/4 times x squared plus 2, okay? Where the product rule states that for f at x equal to uv, the derivative of this function would then be equal to the derivative of our first term times the second times plus, the first term again times the derivative of the second term. Now our first term is a constant, so the derivative would just be 0. So the derivative simply becomes 0 plus 1/4 2x, which is just equal to x over 2. Okay, then we have to evaluate for our equality, where we equate the two derivatives. And we again solve for these two numerically using Newton's method. Factoring the equation yields a less exact answer of 2. So when we find our roots, we find that they come out to be about 1.77276, which is just about 1.77. Okay, and that is all for these questions today.